So here we come to a question of differentiating a function that involves an integral. So if you want to differentiate a function like this, integral from, so let's call this function h of x, integral from x squared plus x to sine x of e to the x squared dx. And the question is to find derivative of h. Well, the simplest way is to try to compute this integral, right, and to try to evaluate the antiderivative. That is the simplest, straightforward way. And if you try to do that, I will try it with Wolfram alpha. Integrate e to the power x squared.
Having a wee bit of trouble. Can you please try it again?
I will try it again. Integrate e to the power x squared.
Let me think. I found this.
So it says it is equal to a half of square root of pi multiplied by ERFI of x plus a constant. Well, extremely helpful information, especially when you know what that function is, right? And what it doesn't tell you is that this function is a strange function that can never be expressed in terms of standard functions, like square root, logarithm, exponential. So basically, this is an example of a function that cannot be evaluated using the functions you already know. So you have to introduce a new type of functions, and this is standard notation for this kind of function. So it is not very helpful in this respect, especially if you have to deal with this function and you don't know what it is. So you may succeed in this, or you may fail. And what I pretend now is that you fail to evaluate the antiderivative, and you have to deal with the original function. And again, I am focusing now on computation, right? I am not talking about understanding of what this is about or any application of that. I'm just trying to compute the derivative. So what do I do now? I would like to apply the fundamental theorem of calculus, because I know how to differentiate with respect to upper limit. The problem is that my lower limit is not a constant. And here's the first thing. Well, first preliminary step is to understand this formula better and to change the notations just for the clarity. To recognize that this x is artificial variable, so let me replace it with theta. And now we see that our function of x has only that variable x appearing as lower limit and upper limit. And then, one of the basic properties of the integral would allow me to write this integral as sum of two integrals. So I will split integration from that lower limit to some constant, and from that constant all the way to the upper limit. So it will be the same as integral from x squared plus x to some constant of my choice. Let me choose 1 of t to the theta squared d theta plus integral from 1 to sine x e to the theta squared d theta. The advantage I'm gaining so far is that one of the functions has constant in the lower limit. The other one has constant in the upper limit, but I can deal with this by switching the limits. If I switch the limits, I get the negative sign in front, and now my function becomes a sum of two integrals with constants in lower limits. So from 1 to x squared plus x, and from 1 again to sine x. And now I'm almost ready to deal with the fundamental theorem of calculus. What I would do is I would denote this by g of x. I will look at this function and separately at that function. Let's call it p of x. And then my h of x is minus g of x plus p of x. Of course, the derivative will be minus g prime of x plus p prime of x. So I only need to find derivatives of those two functions. And I will find those separately. So how do I find derivative of the function g of x, which is integral from 1 to x squared plus x e to the theta squared d theta? Well, what I have to think about is something in the spirit of the chain rule. I would think about g of x as a composition of two things. Well, if I go back to my original function h, it was an integral from some lower limit a to the upper limit b. Right? And now my limits for the h migrated into limits for g and p. So this was my lower limit for h. I will think about it as a. And what I think about now is that my function g of x is a composition of two functions. I compute a of x, and then I evaluate g of a. And now the advantage of that is that g of a is a very simple function right from the fundamental theorem of calculus. It is a function it is an integral from a constant to my variable a of something. And I know how to differentiate that. So I know how to find derivative of g with respect to a. It is exactly the fundamental theorem of calculus. Then by the chain rule, I have to multiply by derivative of a with respect to x. And that is even easier. And so that's the only trick I'm playing. And that's exactly the chain rule involvement in this problem. So my derivative of g with respect to upper limit by the fundamental theorem of calculus is the value of the function at that upper limit. It's e to the a squared. And derivative of a with respect to x is 2x plus 1. And of course, what I want is the derivative as a function of x. I want to eliminate the a from the answer. I know what a is. It's x squared plus x, so e to the x squared plus x to the power 2 multiplied by 2x plus 1. That's the derivative of g. So let me find derivative of p now. If you have any questions about derivative of g? The derivative of p is just analogous operation. For the derivative of p, I look at the function p as integral from 1 to sine x. I consider this sine x as a new variable let's call it b, and my function p of x becomes a composition of the function b of x substituted into p. So the derivative is going to be the derivative of p with respect to b times derivative of b with respect to x. And again, derivative of p with respect to b is the value of the function at b. So e to the power b squared multiplied by the derivative of b with respect to x, which is cosine of x. And now I only substitute x into b. So it is e to the power sine x squared times cosine x. And now I need to put everything together to get h prime. Derivative of h is negative derivative of g minus e to the power x squared plus x squared times 2x plus 1 plus derivative of p Any questions?
Does it matter what constant you pick? You chose 1. Could you choose anything at all? Like, could you choose 100 if you wanted? Could you choose 0?
It's a good question. For this kind of problem, I would like you not to think about it and choose whatever you want. Okay. 0, 1, or anything you want. When we look deeper into integrals, it may happen that the original integral from here to there exists, but, and let's say original integral goes from some point here to some point there on the line, but if you choose a point, a constant, somewhere far away, it may happen that the function that you are trying to integrate is infinite somewhere in between. And the integral from here back there doesn't exist. Your integral from there back to the upper limit doesn't exist. But the original integral exists.
So how did you know 1 would exist in this example?
You would want to choose that constant inside the original integral.
But how did you know that 1 was inside that integral? You just chose 1.
You would have to look at those functions.
Okay. So you just kind of knew that.
Well, yes, I don't worry about this function because this function can be integrated anywhere. Okay. It doesn't have any discontinuities. So, if your integrand is good, in the sense that it's never infinite, it exists everywhere, it's continuous, there's no problem, you can choose any constant. If you have functions like 1 over x, you would want to avoid the point 0. Right? So you would want to look at whether your values are always positive or always negative, and then choose either positive constant or negative constant. But those are technicalities I don't want you to focus in this example, although important technicalities. Anything else? Any other? All right, so that's going to be one of the homework problems for you if you haven't tried it already.